Good afternoon, wherever you may be in your day. Thank you, as always, for choosing to make general chemistry part of your day. This is going to be totally a review, a little bit of practice, make sure we got it. Okay, so what we have here is everything you should have learned from the last videos. 2 videos. 5 shapes. That's all we have. That's all we use to connect things. We connect things in a line, a triangle, a tetrahedron, trigonobipyramidal, which is actually fairly rare, so we really only use 4 of these, and octahedral geometry. So what I want you to do with every time you see a Lewis dot structure, pick your atom, draw your loops around it, count your loops, and once you've determined the loops, it's either going to be 2, 3, 4, 5, or 6. Once you have that, I want you to draw your stick figure. This is our 2, this is our 3, this is our 4, this is our 5, this is our 6. Memorize these stick figures, get where you can draw them. Bond angles associated are 180, 120, 109, 90, 120, 90, 180. That's kind of a memorize. Again, 3 angles inside a circle, 360 divided by 3, 120, 180, you probably know. 109 just going to memorize. Right angle, and then we got our triangle again, so that's 120, and then everything here is a right angle. XYZ space coming together. If you ever need a place to, if you ever forget what XYZ space looks like, find the top corner of a room, look over there, and you got the 3 lines coming together. That's XYZ space. Okay. So I'm just going to go through this orally. You can just rewind, quiz yourself over the next 2 minutes until you are able to do it as smoothly and as easily as I can do it. This picture is linear. This picture is trigonal planar. Trigonal planar. If we have one lone pair and cover it up, what we're left with is something that is bent. This is tetrahedral. If I have one lone pair, I now have a pyramid. So this is trigonal pyramidal, or trigonal pyramidal, depending on your pronunciation. Notice I'm going to change which ones I cover up. If I have 2 lone pairs, I'm going to cover up these 2. Now we're back to something that is bent, like water. This is trigonal bipyramidal. If I have one lone pair, I'm going to cover up this one. This is my seesaw structure. If I have 2, again, notice I'm going to cover up change which ones I cover up. I'm back to pity the fool, I got my T-shape. And if I have 3, and if you never watched the A-Team, I apologize for my horrible pop culture references. I'm sure it's on YouTube. If I cover up 3 of them, I have a line, back to linear. And then over here, this last shape is called an octahedron. If I cover up 1, I'm left with a square-based pyramid or square pyramidal. If I cover up 2, they want to be as far apart as possible from each other. So it's going to be the top and the bottom, and we're left with the square in the middle. That's going to be called square planar. 3 is awfully difficult to have. I suppose if I did, it would look something like that, and that would be your T-shape again. Those are your geometries. That's what you need to know. So let's do a little bit of practice. Look at one larger structure, and we'll call it a day. We're W all experts on geometry. Okay, so again, with each of these structures, regardless of what I give you, sometimes they might be drawn well, sometimes they might not be drawn well to imply geometry. Assume that the picture does not imply the geometry. What if I make you draw your own Lewis dot structure? If you haven't determined the geometry, the odds of you drawing perfect geometry are probably fairly bad. So all I want you to do is take your central atom and draw your loops. Don't miss any lone pairs. That's the easiest thing to do. And this prevents us from double counting double bonds, which also is a common mistake people make. So I'm just going to go and do my little doodles and draw my loops. And all I want you to do is count. So this is 3, 6, 3, 6, 3. Oh, I wasn't very creative there. Probably could have mixed it up a little more. Just pick molecules and put them on the board. All right, so for this, you just draw. For the 3s are all going to be the same. We draw the stick figure with 3. For the 6s, they're all going to be the same, although this works out nicely for board efficiency. I only have to draw 2 of these. I'm going to draw my stick figure with 6. Again, we have to memorize these. We have to know our stick figure. So this is my loops and sticks method. And now for each of these, we just map the molecule on. So we have atom, 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 lone pair. I can't count. Wow. That would be 4, ladies and gentlemen. And the 4 picture, I'll put over here. There's my 4. So we're going to take the 4 stick figure, I apologize, and this is my 4. And we're just going to map that on. Lone pair, atom, atom, atom. So, now what I intend to do, lone pair, atom, 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 atom. And the question is, what shape is formed by what we have left behind? There's my triangle-based pyramid. This is trigonal pyramidal. And my bond angle is going to be slightly less than 109 degrees. Remembering the lone pairs push down more. So that's for that. Now if we want to do the 3 here, we just look again. Atom, atom, atom. So this is going to be all atoms. And this is just a triangle. So this is trigonal planar. And my bond angle is my perfect 120 degrees. If I were to take this with 6, we have 2 lone pairs. Remember, we have to put them as far apart as possible. So I'm going to put one at the top, one at the bottom, and then I'm going to just put my chlorines in and my iodine in. And I get something that would be square planar. And these are 90-degree angles. So again, if you want to do this so you can really see what's going on, I'll put the little chlorines and the ion there. Excuse me, but you get the idea. Down here, we have our stick figure with 3. So again, draw your 3, and then map it out. Lone pair, atom, atom. Lone pair, atom, atom, atom. And you can see the figure that's left is bent. And since we started with 3 sticks, it's going to be a little bit less than 120. This has all atoms. This means we get our perfect 6 structure. So this is just going to be octahedral. And 90 degrees. 180 if you want to be overly thorough. Which is not a bad thing. So that's how you do it. Again, sticks, loops, map it onto your stick figures. Boom. You got your geometry. Alright, so how do we break down something bigger? And this is, I kind of joked around about a protein, and this is, Lord only knows, I don't know, a 10,000th of a protein. It's very small. But for Gen Chem, this can be intimidating, very large. So how do we break down some of this? We would never really talk about the geometry of this whole structure. It wouldn't get its own name. Now we could model it, we could build it, we could use, and we could look at what that surface would look like, and that's fine. And you might do that if you're doing some high-level research, seeing how this bound to an active site of a protein or a drug interaction or something like that. But if we were trying to build this, how would we know how to build it, or how would we look at the pieces? And what we do is you just do this the same way you would eat an elephant. You eat an elephant one bite at a time, and we're going to do the same thing with the molecules. So you just take any of these interior atoms and you pick one. So let's pick that one. And then you just break it down like you normally would. We have 2 things attached to that carbon. This would be a 180-degree angle. And around this particular carbon, we would say it has a linear geometry. Again, our stick figure with 2 is a line. If we were to say, pick a different carbon, do the same thing. Draw your loops. 1, 2, 3, 4. My base picture, and it's atom, 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 atom. So this is 190 degrees. And this is going to be tetrahedral geometry around this carbon. So again, you just break this down piece by piece. If we did this carbon, you'd have 1, 2, 3 loops, 120 degrees. It's atom, atom, atom. So this would be our base structure, which is trigonal planar. If we are finally to the oxygen down here, our last interior atom, we go loop, 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 loop. This is 4, so we got to take our stick figure with 4, and we have 2 lone pairs, so we're going to map those on. And then we got atoms, so we're going to map those on. And you can see this structure is bent around that oxygen. So this is how you would do this. And mainly what I would do is I would talk about bond angles. 180, 109, 120, 109. But you would take each piece and just individually look at it. So I hope that was helpful. Hope that's instructive. This is it for Vespr, other than, I suppose, what we'll do in class and homework and all those things. But last part of the video. Thank you so much. I will leave you with this fantabulous thought to wrap up the summary of what we've done. What did the acorn say when he grew up? Gee, I'm a tree.